Okay, so let me introduce the speaker. Yes, so maybe just say one word how this came about. For some time, I was kind of curious. Is my voice is okay, by the way, Charles? Is my voice okay?
Yes,
Okay.
yes, it's fine.
I was intrigued for quite a while about a possibility of vortex formations in power grids. But I have not been doing anything myself. I just attended occasionally some seminars on this subject. And so because of, because of those circumstances we have, because of magic of Zoom, last year in December, I was invited to give a talk at a big conference on complex systems in December, hosted in Europe. And this conference had satellite conferences, and one of them was in complexity in electric grids. So I attended that conference on Zoom as well. And so long story short, I came across to know that Philippe Jacquod, the speaker today, he is actually the one who studied vortex formations in electric grids, among other subjects other topics on the subject. So I decided to invite him for JQI today's JQI seminar, again, because of magic of Zoom. Because, there is quite, as you will see, there is quite a bit of parallels between superconductors and vortex formation and actually surprisingly power electric grids. Of course, Philippe, he has quite a bit of background in quantum physics, so I'll tell you briefly his CV. He studied physics at ETH Zurich, graduated in 92. Then he was a postdoc in several places, Neuchâtel in Switzerland, in Yale, in Leiden with Carlo Benacher, I believe. So he was doing basically mesoscopic quantum physics, and you'll see some of that in the talk, I hope. Then he became assistant professor at the University of Geneva, 2003. In 2005, he became associate professor at University of Arizona, United States. And from 2013, he switched eventually at some point to study of electric power grid. So I believe he is at Department of Electrical Engineering. Anyway, he studies power grids if I believe it's correctly, it's like University of Western Switzerland. It's hard for me to pronounce exactly the names. And he has a grant from Swiss Electric Power Utility, if I understand. And he also has affiliation with Department of Theoretical Physics at the University of Geneva as well. So anyway, he has backgrounds both in quantum physics, mesoscopic specifically, and in electric power grids. So I think that's exactly the right combination that brings interest to JQI. So anyway, we have a good audience today. Some people from JQI and some people actually from electric grid, professionals. So anyway, I'll let Philippe to start, and there'll be of course social hour after the talk, so to ask questions and all that and have discussion. Okay, welcome.
Sure. Well, thanks for the invitation. Thanks for the nice introduction. Well, there is a good thing about the magic Zoom, as you call it, that we can have this type of events and interact and discuss topics that we would not be discussing otherwise. Still, after 1 year, I'm not that used. This is perhaps my third presentation, and we will see how it goes. As you could see, I had trouble with the arrow and the pointer, so I'll try to make things happen without that pointer thing, and we'll see how it goes. And if there are things that are not that clear, please interrupt me, and I'll be just too happy to clarify. All right, so the original title, okay, so now, was Quantumness in the Physics of AC Electric Power Systems. Now, you see, I've put quantumness here between quotes because, of course, H bar is equal to 0 in this system, because obviously, there's no uncertainty relation. You can actually measure voltage and voltage angle simultaneously. But there will be analogies. So a more appropriate title would have been Coherence and Analogies with Quantum Physics in AC Electric Power Systems. One of them will be the vorticity, and I'll spend a lot of time talking about that has just been mentioned right now. The 5 figures you see on this title slide, this is the representation of the synchronous grid of continental Europe. Every dot is a node in that network. It's either connected to a power plant or to a consumer, let it be a city or something else. And what was done, the colors that you see here are deviations from the rated frequency of 50 Hertz. When it's blue, you have no deviation. When it's green, a little bit, yellow, a little bit more, red, it's a lot of frequency deviation, and black, it's the maximal frequency deviation, following an outage of 2 power plants. And you see that this wave is propagating. There's a wave of frequency deviations propagating over Europe. One thing that you can see is that by the time you get from the left to the right, it's about 4 seconds to go from the left to the right, if I remember correctly. By the time you get to the rightmost figure, you have Spain that is actually in red, which means its frequency deviates a lot from the rated frequency. So the wave has gone to Spain from the east, from the Balkans. One thing you may see also is that the perturbations seem to avoid largely the central part of Europe. And that's a little bit like, you know, some kind of tunneling, if you want to see it this way. You have a wave that goes from one part to another part without influencing what's in the middle. And so that's one of the things that we also discussed beside vorticity in these systems, you know, some sort of scattering with some analogies with quantum physics. But let me start with first things first. Okay, so now there is a, okay, here we go. What are electric power systems? So they include everything from generating power stations down to consumers. And because you want to transmit electric power over long distances, you need to crank up the voltage in between in order to minimize losses. To do so, you are using step-up and step-down transformers because you cannot produce electricity at very high voltage and you cannot consume it at very high voltage for obvious reasons. And so because of these transformers, well, you need to, the capacity, sorry, to crank up and down the voltages is easy in AC with alternative current, easier with AC than DC. That's why Nikola Tesla advocated this AC power grid that we are relying on right now. Okay, so let's see. And you have 7 levels of electric power systems, 3 levels of transformation, 4 levels, extra high, high, medium, and low voltage. Obviously, the boundaries between these different levels is a bit fluctuating depending on the country you are in. Now, I want to understand how these things work. I want to characterize the state of my system. So what I do, I'm going to write an equation for that system. And the equation is going to be an equation for the electric power. Why? Because the power is conserved from one level to another, more or less. There are some losses in transformers, but I'm going to neglect those. And because the power is actually the control parameter for power grids. So I'm going to write an equation for power. How am I going to do that? Well, my starting point is going to identify what are the degrees of freedom. These are, you have complex voltages at each of the nodes, and they're related to currents, electric currents, via the Ohm's law, which is a linear relation, and the coefficients in these linear relations are given by this admittance matrix, this Yij matrix. Off-diagonal matrix elements of the admittance matrix is minus the admittance, that's my definition here, between node I and J on the line Ij. And on the diagonal, you have the sum of all the off-diagonal matrix elements with a minus sign. That's the definition of the admittance matrix. And the current is defined as positive. If you have a power plant, you inject current into the grid, and it's negative. If you're a consumer, you extract current from the grid. All right, so far so good. With that Ohm's law, what I do is that I introduce a complex power. After all, I'm looking for an equation for power, so I multiply all this by voltage. I complex conjugate that expression. Remember that I'm using complex voltages and currents. And when I do that, I can take the active or the reactive power. I can take the real part or the imaginary part of that complex power. What does that mean? If you were solving the problem in real algebra, you would have an oscillating part and an average part of the power. The average part is the active power. The oscillating part is the reactive power, up to a factor of 2 in the definition, I think. So the equation that you end up with all these manipulation is an equation are called the power flow equations, and they are given here. These are coupled transcendental equations. They can be solved numerically only, and they relate the voltages and voltage angles at all the nodes in your grid to the active and reactive power via the conductance and susceptance matrix, which are the real and imaginary part of the admittance matrix. So these are the equations I'm interested in. As I said, transcendental coupled equations, they are hard to solve. In principle, you don't have exact solutions analytically, especially if you have a complex meshed grid. Well, instead, what you can do is actually do some simplifications. And, you know, as a good physicist, I'm going to do some simplifications here, which are the following. I'm going to consider. Okay, so everything is frozen now.
Well, while it's frozen, may I ask a question on this particular slide?
Okay, let me go back here. Go ahead.
Well, yeah, it seems to me that as a system, you know, there are, what do you call it, inhomogeneous terms. That is, the power at a given node, there can be input power or extraction of power. And I'm just wondering, you know, I don't see how this breaks down into, say, like a system of homogeneous equations with some inhomogeneous equations that provide the input. Maybe that's just too simple a way of thinking.
So you see, if we want to go into the details, you have two types of nodes. You have the power plants, the producing nodes, which are PV nodes. On those nodes, you know P, the active power that is injected, and V, the voltage, the absolute value of the voltage. And then you have PQ nodes. These are consumer nodes where you know what is the active and reactive consumed power.
Ah, so Q is consumers and P is power producers, broadly speaking.
No. P is power injected if it's positive, it's power consumed if it's negative, and it depends on the node that you consider. And that's the active power, and Q is the reactive power. Now, a consumer has a well-defined reactive power that they need to function, whereas producers just adapt the reactive power they inject in such a way that they stabilize the voltage.
Okay, thank you. I think things will get clearer as you go on.
Okay. Well, anyway, I'm only very seldomly going to consider the full power flow equations here. I'm going to simplify them shortly. So the thing that you may keep in mind is that actually, if you take very high voltage power systems, and I'm going to specify two very high voltage systems. So think in terms of transmission voltage grids at 200 kilovolts or more, you know, that span entire continents, like the one I showed you in the title slide for the synchronous grid of continental Europe. In those systems, you know, cables, and you see one of these cables here, are pretty big. And it turns out that they are so big that actually you can neglect the real part of their admittance. It's a first approximation that is very common. It's called the lossless line approximation. And when you neglect the conductance, you might as well neglect voltage variations. And consequently, you don't consider the reactive power. You just have this equation for the active power. PI can be positive or negative. Positive if you have a power plant, a producer. Negative if it's a consumer, if it's a if it's a consumer. Now, I assume that many of you have already seen an equation like that. Who can tell me what that corresponds to?
It's Josephson current.
Josephson effect.
It's a Josephson current, right? I mean, Bij sign of the angle difference is like, well, you would have some tunneling matrix element of, appropriately normalized magnitude Bij between two superconducting islands, one at superconducting phase theta I, the other one at theta j. So it's very surprising that actually you have these huge systems, and we are talking very high voltage. So we are talking about these big, huge poles that I'm showing here on the right-hand side. And they are not unlike Josephson junction arrays, which are obviously, much, much smaller devices. And so there is an analogy, and that's the first thing, perhaps that I noticed when starting to work in that field. Can it be that, you have effects that occur in Josephson junction arrays that also occur in high voltage AC transmission power grids? Yes. So the first thing that you may ask yourself when you look at these power flow equations is how many solutions are there to these power flow equations? Again, these are transcendental equations. In particular, they're not linear, so there may be more than one solution for different geometries, for different PIs and QIs. And it was recognized early on by a guy called Korsak in 1972 that actually, if you have loops in your grid, you may have different solutions. You see in the left-hand side panel, panel A, panel B, you have two solutions to the same problem where you inject and collect alternatively on the edges of an hexagon. And the bottom solution is obtained from the top solution by adding some circulation of power. That's how we called it. Now, back in 1972, there was something very funny in this IEEE literature that they would publish referee reports, even including names. And there was one Gerd Lüders from Yale University who actually found this article very interesting. And he even pointed out that the difference in the two solutions comes about because you may have a sum over angle differences going around the hexagon, which is a multiple, an integer multiple of 2 pi. So he was the one in that referee report to introduce vorticity, let's say, as I would call it, in the power grid literature. And then nobody else did anything. But one thing happened later on, in the mid-90s, they started to see loop flows in the United States power grid. Along the lake area, you have a big loop, and around that loop, they would see, loop flows that can drive as much as 1 gigawatt of power in a circle, taking up transmission line capacity without delivering power to consumers. That's pretty amazing, right? I mean, you have 1 gigawatt of power, you have thousands of amperes of things that are similar to a supercurrent around lake area. So I don't have a definite answer for whether this was really truly a vortex that was created there. And the reason is clear that, the different communities work differently. It's extremely hard to have data, to put your hands on data in that business, which is actually a business. And that's why, data are not shared that easily. So the only thing I know, though, is that around that lake area loop, they have like 4 or 5 operators. And each of them observed at that time 1 gigawatt of power flow that they were not expecting. And so each of them looked at the direction of that flow and called the operator before them to ask where that power was coming from. And then going around the loop with their, calling each of the guys before them, they realized that actually it was a loop flow. It was really a circular flow. How could you actually understand such a flow? Well, let's go back to the Landau theory of superfluidity, superconductivity. You have a complex order parameter, and I will make the analogy with the complex voltage that I have in my system. Then you have two cases. In the first case, superconductivity is everywhere. In the second case, superconductivity disappears somewhere. Now, in the first case, if you calculate a circulation integral of the gradient of the phase of the superconducting order parameter around the closed loop, that must give you 0. Why is that so? Well, first, you want the superconducting wave function to be single valued. So the angle when you go around that loop can vary only by an integer multiple of 2 pi. The angle being a compact variable. But then it has to be 0 because by continuity, you could actually shrink your contour of integration until it becomes only a point at which stage you are forced to set the gradient equal to 0. Well, you cannot have this continuity argument if the superconductivity vanishes somewhere. Around that somewhere, you can build a loop, and there may be cases where suddenly you have an integer, a winding number q, representing, the variation of that gradient of the phase of the superconducting order parameter around that contour. And so that's how, vortices are born in superfluidity and superconductivity. And do they exist as well in our problem? So let me get back to my power flow equation, and I look only at the simplified power flow problem here. There's a theorem that tells you that actually if you have two different solutions to that power flow problem, they differ by circulating loop currents in any network. Well, in any network that has at least one loop, in any meshed network. Now, that was shown by us in 2016, and then the referee told us that it had been shown earlier, so we found that paper by Dörfler, Cherkov, Bullo. In the supplementary material to that paper, you actually find that proof, so we had missed it. We knew that paper beforehand. So what are these loop flows? I mean, you can consider one loop, as is shown on the right-hand figure here. And if you have P1, 2, P2, 3, all these flows that are defined, you may add a constant flow to all those guys and look at how this translates into different angles. If the angles are still well defined, then you have a second solution. That's truly what this loop current means. And so the physics is the same. Here we don't even need to actually calculate a contour integral because, I mean, the system is discrete. You go from one node to another, and you just add the difference in angles. So if you look at my definition of the winding number there, the vertical bars around the difference between angles, they stand for, difference of angle modulo 2 pi. I define them from minus pi to pi. And if I do that, I can have a winding number Q that can take any integer value depending, well, on a number of ingredients, which I will discuss later. Okay, so these are the vortex flows, and we know that these are different solutions to the power flow problem. And I'm just illustrating this on a more complex power grid. You have here the British power grid. You have two solutions on the left-hand side. And when I take the difference, I get the solution, I get what's on the right-hand side. And if I zoom in, I see that there is a loop flow around this big geographic loop you have in the middle of that network. Okay, so we have established the existence of those solutions. And at this point, let me just make a summary of what we've seen so far. You have an analogy between superconductivity, let's say, and high voltage AC power grid. The state of superconductors is represented by a macroscopic wave function. It's represented by a set of voltages, of complex voltages in high voltage power grids. You have current power flows, Josephson current in the case of superconductivity. If you have, well, you would have an array of superconducting islands. You have the power flows in the lossless line approximation for high voltage power grids. You have winding numbers which give you flux quantization and or persistent currents, vortices in superconductors. You have circulating loop flows in high voltage AC power grid. Now, of course, the main difference is that you can measure the angle, voltage angle, and the voltage, the amplitude at the same time in a power grid, and you cannot, in principle, measure the two in a superconductor. Okay, but now that we know that circulating loop flows exist, the question is, how many of them are there? How many of them are stable dynamically, and how can one generate them? And if I want to answer those questions, I need to move on to actually construct some dynamical model for my power grid. And this is what I'm going to do in the next slides. So what a power plant does is actually two energy transformation. First, from some sort of energy, which can be potential, chemical, nuclear, thermal energy, that you convert into mechanical energy. And the mechanical energy is actually the kinetic energy of rotation of your turbine. And then there's a second conversion of that mechanical energy into electric energy. And so with these two conversions, I can write a conservation, let's say a law of conservation or variation, let's say, of the kinetic energy of rotation of my turbine. And that's what I'm going to write. Well, I'm going to use power instead of energy. That's what you do in those systems. And what you do, what you get then are called the swing equations, which I'm going to flash you here. So there are two terms on the left-hand side, which are, derivatives, second derivative, first derivative of the angle of the voltage angles. The second derivative of the voltage angle comes about because you took the derivative with respect to time of the kinetic energy of rotation of your rotating machine. So I is, in some units, it's inertia. The first order term is damping, but I mean, you need to understand that these equations are written in a rotating frame at 50 Hertz in Europe, 60 Hertz in North America. That means that this damping doesn't damp you down to no motion at 0 Hertz, but it damps you to 50 or 60 Hertz. So that's not physical damping, it's not friction, it's actually control. And it's built in on some of these machines that we have. And then on the right-hand side, you have a balance between injected power, which is the PI, for instance, or collected power, and the power that flows through the grid away from the node number I. When this difference is 0, that means there is as much power going in as going out. The angle the frequency doesn't change. The derivative of the angle is 0. The second derivative of the angle is 0, and I'm back to the original, power flow equations. Okay, and just some technical reminder about these power grids. The change in kinetic energy reflects the balance of power. So by monitoring the frequency of your grid, you know whether someone somewhere is consuming too much or is producing not enough or too much.
Philip, may I ask a question on this previous slide? Just wanted to clarify, for my kind of education.
Sure.
Is it really that, that was my puzzle. Is it really that all those turbines, being hydro or nuclear, do they really rotate at 50 or 60 Hertz? Meaning, naively, I would imagine that their optimal operation frequency, conceivably could be very different from 50, 60 Hertz, right? Depending on design, on efficiency, etc. but then of course one will have to have some kind of frequency conversion, adjustment to 50-60 hertz. So is it really the case that all those power plants machinery actually rotates at 50-60 hertz, or it may be different?
There are different types of machines. Right. I mean, the original machines that were rotating at 50 hertz or a multiple of that, depending on, how many poles you have on your machine. Right. And now more recently, a rotating machine has a rotor and a stator, and the stator is also sometimes also rotating to actually adapt the frequency of the machine. Because obviously, if you take a hydropower plant and you want to make it function at higher power, so you would just open and let more water flow through it. In principle, that may accelerate the turbine. Now, some turbine will just generate more power and remain at the same frequency. Some others would have a different frequency, which would be adapted by the stator, which is no longer static. And then there are other types of machines. So, but originally all the machines were rotating at the same frequency, and that gives this coupling between the mechanical degrees of freedom and the electrical degrees of freedom, actually.
Yeah, so my point is that basically, right, original machines were 50-60 hertz, but more recent machines presumably rotating at whatever is optimal speed of rotation, but then there's adaptation of frequency adjustment, either mechanical by stator rotation, or maybe some electronic. I mean, I could imagine some electronic frequency conversion, maybe. Yeah.
Oh, well, okay, if we go into power electronics, then, the sky's the limit, and we will talk until midnight tonight, right?
Okay.
Your time. But yeah, you're right. Just one more remark here, because we were talking about these wind turbines that were responsible for this Texas blackout, or so they say. They have mechanical inertia, they rotate, but that mechanical inertia is not connected to the electric frequency because of multiple conversion. You have power electronics that converts the signal into DC current first and then back to AC at the frequency of the grid.
Okay,
so it connects. They have no inertia in those equations here.
Okay, so it's actually AC to DC and then DC to AC. Okay, that's how it really works. Okay.
And there are other examples. There are many, actually, if we were to build the power grids nowadays, we would do it very differently because we have power electronics. Nikola Tesla didn't have power electronics, so he had to rely on, Maxwell's equations, Ampere's law, and the law of induction. So that's why, there was this AC grid. We would probably build a DC grid right now. All right. Shall I move on?
Yes. Yes.
Where am I? Okay. So you see, the thing is similar to a model in dynamical system, which is very popular when you study synchronization. It's the Kuramoto model, which is the harmonic oscillator of synchronization. If you want, you have a set of oscillators with a natural frequency pi, and are connected to one another with some strength, and also with that term, depending on the sign of the angle difference between the oscillators. And depending on, the balance between, the natural frequency or the distribution of natural frequencies over your grid and the strength of coupling between the oscillators, you may or may not have a synchronous state. So that's really a balance between the two. And the coupling in power grids is given by the capacity of the lines and the natural frequency of the oscillators in power grids. These are the power produced or consumed at that given node. So there is this analogy, and obviously, when you want to operate power grids, you want to stay at a stable synchronous fixed point. That's your goal, and if you can achieve that goal, I mean, safety of supply is assured. Okay, So now we have the dynamics. Let us look at how many circulating loop flows there are and how many of those are dynamically stable. And I'm going to go relatively fast through that. What you need to look at is a solution to that equation around where you sum over angle differences modulo 2 pi about a loop in your grid. So if you want to know how many solutions you have, well, the first thing you can say is that the right-hand side is bounded by the number of edges in the loop, the number of consecutive angle differences you can sum, times pi, because these angles may differ by pi at most. And so that gives you a number of solutions which is bounded by twice the integer part of n over 2. Capital N is the number of nodes I have around my loop, plus 1. But I mean, it turns out that actually most of those guys, or many of those guys, are actually unstable because they correspond to angle differences that are too large. The coupling is proportional to the sine of the angle difference. If you calculate stability, you need to take the derivative of that. You look at the Jacobian of that coupling matrix, and that Jacobian is cosine of theta I plus 1 minus theta I, which becomes negative when the difference in angle is larger than pi over 2. So a rule of thumb is to say, well, as soon as you have angle differences that are larger than pi over 2, as soon as this arc sine function, I mean, as soon as you are above, beyond the maximal variation of this arc sine function, well, forget about the other solutions, they are not stable. Okay, and that comes about with the calculation of the stability matrix and spectrum. So instead of having angle differences that can reach up to pi, they can reach up to pi over 2, and we have that bound here. And if you have a single loop, that's a pretty good bound, actually. In most cases, that's what you have. And of course, the number of solutions is going to disappear as the coupling strength between oscillators is going to be reduced. You have all these solutions in the limit when the coupling strength is infinite. Okay, and of course, when you go close to the bifurcation, there are a number of caveats, but I'm not going to discuss them in the talk. Maybe we can, if someone is interested in such details, we may discuss that later. Okay, now what happens if we have meshed graphs? Now you see the problem is the following. If suddenly you have added to, let's say, the left-hand side loop here, you have added a relatively large loop flow that goes clockwise, and the large loop flow to the right loop, but that goes counterclockwise, the two loop flows are going to add in the common segment, and that may lead to an instability. So you would be tempted to say, well, if I have loops, I just take the number of solutions I have here. For each loop, I multiply them, and then I get the total number of solutions, but that's overestimated, and by far. But that's the only thing I can say. This is a problem, I suggest someone solves one day. We were not able to actually take into account of this constraint in generic meshed graphs, let's say. So this is not a tight bound, multiplying the number of solutions for each loop. It strongly overestimates the number of solutions you have, but we could do no better. Okay, so far for the number of circulating loop flows. And now comes the question, how can one generate them? And we identified 4 mechanisms to generate them. First, you may change, first and second, you may change the topology of the grid. You close, you open a line, sorry, or you open a line and you reclose it. I'm not going to spend too much time on that because, this is basically a numerical observation and we don't have a, deep understanding of those things. I'm going to talk mostly about points 3 and 4 here in the remainder of this talk. I'm going to talk about dynamical phase slip, That's how we call it. And fluctuating power injections that can actually drive you from one of these fixed points to another of these fixed points. Okay, let me start with dynamical phase slips. So there is something in superconductors, small superconductors, when you reduce their dimensionality, or at least reduce, some geometric dimensions, which is called quantum phase slips. That's how actually superconductivity disappears, let's say, as, for instance, you make a system, a thin film, a bulk superconductor, you turn it into a thin film. There is a superconductor insulator transition that proceeds with that. And it has been, investigated by a number of people, and I'm mentioning here two papers, the paper by Lau Markovich, Bokrat, Bezredin, and Tinkham, which is a mostly experimental paper. Then there's a paper by Maitveyev, Larkin, Glasman. I'm not going to talk too much about those papers. There is a paper that is a bit more interesting here, well, more directly related to what we do, which is that paper by Rastelli, Pop, and Hecking, 2013, where they looked at a single loop, Josephson junction loop. And that is, very similar to the loop we had before. So what they say is the following, at some point, depending on the magnetic flux, what you may have is that there is a quantum phase slip that actually eventually will destroy the supercurrent through that loop, simply because one of the superconducting island will have its angle, its superconducting phase, wander about by 2 pi, while all others are going to wander in the other direction very, very weakly. And this is very similar to what we will observe in these power system models of ours. So in the Josephson problem, what you have is the classical Hamiltonian that defines the winding number. And you have a perturbation because, you have some charges on the superconducting island. And that's this perturbation that actually drives the quantum phase slip. If you go to the power flow problem, what you may have is loss of stability of some winding number states before others. So I'll show you a system that we devised to actually illustrate that. The two figures you have there, let's look at the figure B first. On the vertical axis, you have the winding number. And you have states with winding number ranging from -3 to 3 for the system I consider. And the length of these segments indicates how far, as a function of one parameter, and it will be some injection somewhere along the grid, as a function of that parameter, how far are those systems stable? Are these winding number states stable? Stability is lost because, well, if you look at the stability matrix, that's the Jacobian again of the couplings between different oscillators. When you look at the spectrum, you see that suddenly you have the largest non-zero eigenvalue that actually goes positive. That's what you see in panel A that I'm showing you here. So you have some sort of, asymptotic behavior where suddenly this lambda2 goes up. Lambda2 depends on the winding number. It's a stability matrix about a stable fixed point, and I'm considering different fixed points with different winding numbers here. And what you see with the arrows is that, for instance, if you go on the red line, cranking up your parameters P, you go up until you lose stability. At the moment when you lose stability, well, your system has a transient that is determined by these swing equations. And after that transient, you end up on the Q equal to -1 winding number state. Now, when does this happen? You need to have a system that has some asymmetry and that has large enough loads. So look at the system I'm flashing you here. It's a single loop. You have one injection and one consumption. You have 1 plus P, 1 minus P. but they are not symmetrical about that loop. The asymmetry is actually of utmost importance. Now, suppose that you crank up P and minus P. Well, you crank up P, more and more production, more and more consumption. There will be more and more flows, larger and larger flows. And these flows will go clockwise from P to minus P and counterclockwise from P to minus P along a longer path. Eventually, if P is large, you will have large angle differences to carry those flows. And large angle differences, when you sum them up over a longer distance on the left-hand side, the counterclockwise path, that will lead to a finite winding numbers. Only the Q equal to -1 state is going to be able to sustain this large P. Okay, so that's qualitatively, that's what happens. And now we can have a look at how these things happen. I have this representation here of this system. And on the top right, what you have are the local angles put on a cylinder from 0 to 2 pi. And the blue lines tell you, how to calculate the angle difference between neighboring states. You go about the shortest path about the cylinder. And that shortest path can change, right? Now, I'm increasing P, and what I see is that the angles start to move. And you will see that one angle corresponding to the location minus P is going to suddenly be rewired very differently. Here it goes. And at that moment, you see one angle wandering, just like for quantum phase slips, and you have Q in this transient oscillating from 0 to -1 until eventually you stabilize at a winding number of -1. So you see, there's really this analogy with these quantum phase slips in the sense that a single oscillator is doing most of the job, and all others are just moving some relatively small amount about their initial value.
Philippe, so may I ask you, so on this figure, there is this ring, there is injection point and consumption point. Yeah. A couple of questions. First of all, other nodes are basically the same, meaning the parameters, the connection amplitudes are the same, right? Uniform. Yeah. Okay. And so on this figure of this ring, just for curiosity, where is the point where phase slip happens? I mean, on which node, as you mentioned, in this ring, on the picture, phase slip actually happened in this simulation?
I think it's at -P.
At -P. So the phase slip happened at -P. At the point where two things connect, that's where discrepancy, frustration occurs, and that's where phase slip happens. Okay.
And at -P, that's if you have a point where you want to receive power from both sides, you have this spike. That's why you see this spike.
So the consumer is at this moment of phase slip, the consumer will receive a spike, will observe a spike, right? No?
If you recall, yeah, well, you see the spike in the angle difference.
In the angle difference, right. Okay, so basically there are two ways to get power, and they kind of wind with different rates, more or less. And because they wind at different rate, then phase discrepancy occurs.
Yeah, during the transient, they wind at different frequencies. Yes.
Okay. Okay.
Okay. So of course, that's the similarity, and I just wanted to flash, some of these references on earlier works on quantum phase slips in a condensed matter, more quantum mechanical setup. This was a sort of toy model, so I'm just flashing you here this illustration, also of generation of one of these vortex states in a more realistic power grid, which is the British power grid. So we already saw that there is a relatively large loop in the middle of the grid. And what we do here is actually not this dynamical phase slip simulation, something that is more relevant to power grids. We make a line tripping and reclosure. So suppose you have a fault for some reason, And the line where we have the fault is indicated on the right-hand side by this arrow. Now you cut that line, you open that line, and the power that initially was flowing, let's say, for instance, from south to north through that line, has to be diverted to the other side of the loop. And cutting that line occurs at about, a time of 100 on the left-hand side. So you see that step there for the winding number, and the winding number is as a dashed line for some time before we reclose. There's no truly winding number if the loop is open. And when we reclose the line, the winding number remains at Q equal to 1. Now, what happens in that grid is that not only do we have the lossless line approximation, but we also have the conductance term, which corresponds to dissipation. And dissipation means that there is an additional power that you need to give to the system. And initially, that additional power that is, burned in ohmic resistance is about, in the appropriate units, if you look at panel D, it's about 0.65. And once you open that line, it goes all the way up to 0.95. So it increases by 50%. And it even increases further when you reclose that line up to 105. So you have, 50, 60% more power losses in that system once you've generated that vortex flow. And the problem, the surprise actually for us, is that even if you try to decrease delta P, well, you remain in that state. You don't lose winding number. You don't lose vorticity by getting rid of this additional power that you need to give to the system. What you achieve instead is that you see that all the angles actually start to rotate because the frequency is no longer 50 Hertz, it's lower than 50 Hertz. You did not, you don't have the balance between power in and power out. Okay, so that's really like there is a topological protection. Even when you have losses in your system, even if you're not sort of like Josephson, right? You have a Josephson system here, but with dissipation, let's say you would have like some resistances in parallel to all the lines. Well, even in that case, well, your vortices are there and they are topologically protected. Eventually, if the losses are too big, eventually you will lose those states. That's for sure. Topological protection is not forever, right? I mean, if you had a sufficient amount of disorder in any topological insulators, there won't be topological anymore. We know that it's up to a certain level, and that's the same thing here. I mean, provided that your conductance is not too large, you will still have those states. Okay. How am I doing on time? Do I still have some time to discuss this last chapter here? This last paragraph?
Yeah, I think you have like
yes, I would say we should conclude in 5 minutes if that's possible to allow for some discussion.
Okay. Yeah. So I'm going to do my best. I'm not good at timing when it comes to a Zoom presentation. I mean, I will need another 5 years of experience, and I hope they won't give it to me. Okay, so let's look at the problem of generating vortices from a different standpoint. So we have these equations here, and if you look at the right-hand side of this swing equation, you may write it as the gradient of what is called the Lyapunov function, and I wrote the Lyapunov function here. Okay, so the gradient of that function is actually very important because it tells you, if you have minima of that function, this minima will correspond to a fixed point of your synchronous fixed point of your system. So I'm showing you on the left-hand side for a simple system, a plot of these Lyapunov function. I mean, obviously, if I have, hundreds of nodes in my system, I should plot this Lyapunov function in a 100-dimensional system, and I cannot do that. So here I have a simplified system, and I'm just showing you this Lyapunov function as a function of two different angle differences. And what you see is that you have 1, 2, 3, 4 minima that are shown in this plot, corresponding to 4 different winding numbers. And now if you want to generate a winding number, say you would start from the Q equal to 0 fixed point, well, what you would need to do is actually go over the path, this saddle point that you see in the middle of the figure, to go, for instance, to the Q equal to 1 solution. And how can you do that? Well, you can do that if you add some noise. Oh, I made a mistake here. Okay, so you can do that if you add some noisy term. Let's say Pi, instead of being constant, is Pi plus some noise. That's a problem of stochastic escape that is relatively old. You have contributions from Kramers in the 40s. Mark Dickman did a lot in that, actually. And my old director from head of the department from Arizona, Dan Stein, as well. I haven't shown him here. Number of people have looked at it from the point of view, which is ours, of coupled oscillators and how you can go from one solution, one fixed point solution to another. Okay, the problem, of course, is that it is highly dimensional. So I'm adding that noise there, and the noise is defined as with its first 2 moments. And yeah, okay, so I had an equal to delta, which is here. And the problem is to look at, when are you going to move from the bottom of one of these wells to the top, the saddle node, connecting one of these wells to another? Well, we have an escape criterion. Just calculate, using that equation that you linearize, for instance, the mean square deviation of the angles. And then look at when this mean square deviation is comparable to the square of the distance between the fixed point and the saddle point. Now, of course, the saddle point, it's hard to actually identify it. And so what we did was just to say, well, by the end of the day, in our calculation, we have a free parameter, which we believe is of order 1, and that will give us our escape criterion. Now, you can calculate the mean square deviation. I skipped the details. You linearize that equation up there. You make a spectral expansion of the angle deviations, and you have a number of Laplace integral to calculate. These are exponential integrals. They are not that hard to calculate. And by the end of the day, you end up with some expression as a function of the spectrum lambda alpha of the stability matrix, the Jacobian of the coupling, the noise correlation time tau naught, and these parameters, unfortunately, m is equal to I in the swing equations. That's the inertia, and d is equal to capital D. That expression doesn't tell you much, but you can calculate it and you have it. Now, if you have a single cycle, you can actually evaluate the distance between a fixed point, a stable fixed point, and the next saddle node as a function of the number of nodes on your loop, and that's the result that is given here. And if you equate these two guys, then that gives you an escape criterion. Why am I repeating this? Okay. And the question of interest now is not to calculate the probability of escape, but the time of escape. How long should you wait with that noise turned on in order to escape? And what we have here is actually 2 different situations. Let's look at the figure on the right-hand side. The blue line corresponds to the case with inertia in your system, and the red line without inertia. And you see that you have these different escapes that occur quite often when you have some inertia, because what I have there is a noise with relatively long correlation time. And we want to get an expression for the time between 2 such consecutive escapes. I'm skipping some details. I'm just taking that I have, after a certain amount of time, I have a distribution of angle deviations, which is a Gaussian, with a variance given by what I calculated before. And then I have this parameter beta, which is a number of order 1, which multiplies my distance to the between the stable initial point to the saddle point, and I do this integral here. I can do this integral. That's the blue line on my figures, and the red crosses are numerical data. And you see that this gives you like this super exponential behavior. The escape time grows to infinity very fast as you reduce the amplitude of the noise. So it becomes, rarer and rarer to actually escape and generate your vortex states with very weak noise, and that's what you expect. What you may not have expected, I guess, is that this simple Gaussian calculation gives you such a nice result. Okay, I think I'm going to stop here. Oh, just one comment here. In this particular type of escape, what we found actually is that, as before, you have very, very few angles, but in this case, 2 angles that actually wander from 0 to 2 pi to generate that finite winding number, whereas all the other angles are just randomly fluctuating weakly about their initial value. Okay, I think I can stop here. This is what we will do next. One direction of research will be to actually see if we can actually anticipate these rare events. There's been a recent paper by Piragas and Piragas that applied some machine learning type of algorithm to anticipate rare events in actually deterministic systems. Can we do that with some weak noise? And we have some preliminary results that seem to indicate that this would be possible, but it's too early to tell you more about it. And the second type of direction of research that we have is this long wavelength coherence, which is very different from what I did in mesoscopic physics, where you are always considering very short wavelength scattering because your electrons are the Fermi energy. So here in these continental size power grids, what you have are giant waves, let's say in this case between, in orange, Spain and Portugal, and in blue, the Balkans, and they oscillate coherently with one another. They have been observed actually by operators, and this is something they really want to get rid of, and they don't quite know how to damp them efficiently. So we're investigating that right now. Okay, let me finish with a disclaimer. Most of what I told you about is fun for physicists, but it's not really relevant for power grids. And the reason is that, with power grids, you will never get close to the true instability, angle instability. When angles exceed 20 to 30 degrees, lines get cut, lines get open. That, you have like safety measures, control measures that come into the game. And unfortunately for us physicists, that means that, what happens at larger angle differences closer to pi over 2 does not occur. But anyway, there are a couple of things that got the interest of some people, including Swissgrid, which is the operator of the Swiss high voltage power grid. So we are getting some money from them. So part of what we do is actually relevant to them. And so I'm thanking them for their support, including the Swiss National Science Foundation and ARMA Suisse. And I thank you for your attention. That was, again, my third experience as a Zoom speaker, and I hope it was not too bad. Thank you anyway, and I'm glad to answer your questions and start the discussion.
Okay.
Thank you very much. Well, anyone who wishes to address the speaker, just please speak up.
Yes, this is Jerry Fitzpatrick. I'm with NIST and connected with the JQI. That was a great talk. I really appreciated it. And I have to make a comment. And it was about a slide you showed where there was a vortex of electric power flow around Lake Erie.
Yes.
And there was a huge power outage in the northeast part of North America in 2003 that slide is actually relevant to, because that slide showed a sort of normal power flow around the lakes out of the US into Canada, back into the US, due to a predominance of hydropower in Ontario and a predominance of load in New York City and other places in the US. And there was a power line that went out, as you said, it was protected, and there was a short when vegetation had been grown into the line and caused the short, and that tripped the line. And that set off a sequence of events that led to 50 million people being out of power for as many as weeks. And what happened was, when that power line went out, the power in the vortex reversed direction. And that set off a lot of protective equipment that did it. The outcome of that was a project at NIST, among many other things. I mean, there were recognitions that the power grid was poorly monitored, that these separate entities that monitor them couldn't really see into each other's territory. And it resulted in something called a phasor measurement unit. I don't know if you've heard of that, but sure. It's a power monitor that's now deployed in the grid. Your introductory slide showed, the change in frequency over a period of, I think you said 4 seconds, over the European power grid. Like that's sort of typical. The older monitoring systems measure voltage and current power flows roughly every second up to about every 4 seconds. But these phasor measurement units measure them 120 times per second. Yep. And these were deemed as a real solution to preventing that from happening again. And the reason it occurred was because the other system operators couldn't see what happened in the grid. And so NIST began a program in that. By 2008, there was money flowing from the federal government for grid modernization called Smart Grid. And it just became a huge issue. But just to give you a little background in how these vortices sometimes have huge impacts.
Thanks a lot. Do you have any documentation I could put my hands on about that event? One of my frustration in that field is that it's very hard to actually get data. I mean, now I'm friend with Swissgrid, so they give me good data. But it's very hard to get. I mean, you really need to know someone who actually is going to pass this on. It doesn't function like science, like physics.
Because of business models. I mean, there are liabilities for electric utilities, and so they don't want to expose themselves by releasing data that they could be accused for causing a power outage. It's been our frustration for many years as well. We tried to form a collaboration. There's something called the North American Synchrophasor Initiative. We tried with them to get a collaboration of utilities that would anonymously provide these data. It just is too hard to get. There is publicly available data through something called FNet, which is a nationwide monitoring system, but only for grid frequency. Basically, they're plug-in devices that you can plug into your wall socket. It monitors the frequency, reports it via the internet to a central location in Knoxville, Tennessee, and it's time-stamped. So the time progression of frequency changes throughout the North American grid can be monitored. But again, it's not voltage and current because it's in the wall socket. it's not in the grid.
I've seen that they have pretty impressive data on YouTube. You can see movies of like frequencies, waves across the United States. I really like that project.
The propagation of disturbances. Mm-hmm.
That's right. But I mean, if do you know if there is like a report on that outage that you mentioned in 2003?
Mm-hmm. I will certainly do that.
Okay, that'd be really nice. Thanks.
Yep. Yeah, I also would like to get this information. I mean, I also heard about these phase measurement units in the United States. I communicate with somebody, Department of Energy, and they say there was actually a website, a web link to this PMU, phase measurement units in North America. What I'm not quite sure to what extent data, my understanding is these units, phase measurement units, have been installed. I mean, a network has been installed, right, in North America.
Yes.
Whether data is available, that's not entirely clear. But I wonder in Europe, do they also have like phase, not frequency? Frequency is easy to measure. The question about phase, which is non-trivial, is there a phase measurement like unit network? Is it in Europe as well?
Yeah.
There are. I just am not as familiar with it. I don't know how many are installed. In the U.S., there are several thousand phaser measurement units installed now. The federal government paid for a lot of that. But in China, there are far more phaser measurement units because their grid is relatively new and all of their new installations are required to have phaser measurements.
It would be really great to get access to this data for research purposes because, we have all these theories. Most of us are theoretical physicists. We play the theoretical models to compare with the actual data. That would have been...
it's what we all need.
Especially because government paid for it. So, I mean, again, that's a story. Government pays for this installation, so it should be accessible then. Yeah,
it gets sticky. But
yes,
it should be accessible. No. You're right. But it was actually 50-50 cost shared with
Yeah. Okay. And on that subject, if I may also, how often this events happen? For example, I received a message. I communicate with somebody else, researcher, and it was mentioned that let's see, what was that? There was this event of. Normally operators want frequency to be locked, so in synchronized, synchronized state. But desynchronization does happen. So somebody told me that in January 8th, this year in Europe, there was desynchronization event. So it separated, and the frequencies were different. They were desynchronized, and no power was flowing. My understanding was not because of physical connection. There was physical connection, but because frequencies and phases were desynchronized, there was no net flow. So what this event, January 8th this year, can you say something about that? No?
Yeah, so it was a disconnection between, the eastern part and the western part, and the line was along, let's say, former Yugoslavia to Poland, something like that. And if you look at the grid there, you have 7, 8 different lines that flow across that disconnection line. And so there was an event at some point where the frequency went up a little bit too fast at some substation which was connected to one of those lines. And so it's what is called rock-off, right? Rate of change of frequency. And if it exceeds something, something like 0.5 hertz per second or something like that, or perhaps a little bit more depending on where you are, then the line is opened. And so there was a measure like that. And 2 of these 7 lines were opened that were carrying a significant amount of flow. Flow was redistributed. I mean, the eastern part of Europe was overproducing and the western part was underproducing. So there was a east-west flow. And because you redistribute the flow to other lines, the other lines were also disconnected. Now, what is actually very surprising is that it just disconnected the grid into 2 pieces. And nothing else. There was no blackout. So the frequency was a bit above 50 hertz in the east and below 50 hertz in the west. So what they needed to do is to reduce the production in the east and reduce the consumption in the west, so that you bring the 2 frequencies to 50 hertz and reconnect the two parts. Now, I'm no expert there, but I hear that it's very hard to reconnect, simply because it's not only the frequency that needs to match, but it's also the angle. If the angles are widely different, you have a huge current on the line at the moment you reconnect. And they managed to do that in a limited amount of time. I think it lasted a few hours, and then they reconnected. To the top of my head. But that was really interesting. You know, if you want to go to the condensed matter analogy, it's a little bit like taking two Bose-Einstein condensates and moving them apart, and then their phase shifts, and you want to put them together. You know that you will generate this Kibble-Zurek sort of vortices at the boundary, and you cannot afford to do that in the power grid. So you need to restore first the equilibrium between the two phases and the two frequencies.